Okay, so the second module is more on uranium lead methods. So this is about how we actually measure these things on a mass spectrometer. We're going to get, as I mentioned before, a lab tour in a bit, where we're going to get to see the instrumentation that's doing all of this work. Okay, so the way that this works is on mass spectrometers, it turns out that they're really good at measuring ratios between isotopes of the same element. So lead-206, lead-207, no problem, reads a great ratio. Keep in mind, those have similar ionic radiuses, they have similar masses, and so they're going to behave really similarly in the mass spectrometer. So the laser pulses down, it ablates material, the carrier gas comes in, it brings it down, it brings it through the plasma, they ionize similarly, they go through the flight tube. We'll see all of that in more detail here in a bit. But all of those two things behave really similarly, and so we end up with this really small mass bias that we need to correct for. So that's really different than isotopes of two different elements, which is what we want to measure when we're measuring, say, uranium-238 to lead-206, right? So here, these things don't behave anything like. From drilling the pit at the beginning, turns out uranium-238 much heavier, it gets stuck in the hole, it doesn't come out as easily as lead-206 does. So we have this huge fractionation that we have across as these two analytes are measured. We have to correct for that, otherwise our ages are just completely off. Okay, so we have two methods that we can use to correct or to calibrate these ages. The first one is called isotope dilution TIMS. So the way that this works is we take crystals, and then say zircons, that's my default. We take zircons, we dissolve them, we add a spike of non-natural isotopes, so things that don't occur in nature. We chemically purify those, and then we toss them onto this TIMS. We can measure the amount of spike, we can measure the amount of inferred other isotopes, and then we can actually correct that. We'll see this in the next slide as well. The other way that we can do this is called standard sample bracketing. This is the method that we employ on ion probes and on laser ablation in particular coupled plasma specs. So the way that this works is we want to measure zircons and we don't want to put them in solution, right? That's a lot of labor. George used to do this for detrital zircons, dissolving hundreds of grains. Yeah. So we don't want to do that. So we're going to keep our samples whole. We're going to keep the crystals solid. So the way that we're going to correct for this is we're going to ablate or sputter the crystals, right? We have our laser or our ion beam coming down. We're going to measure the isotope ratios coming off of our crystals. But then we're going to calibrate this by comparison with standards. So we know, just for example, we have these green standards here. We know what their ratios should be. We're not measuring the correct ratios, but we're going to correct back to what they should be. And then we're going to take all of our unknowns along for the ride too. We're going to correct those using the same amount, the same fractionation that we're correcting our standards with. Okay, so there's a lot of steps on this slide. This is more on ID TIMS, more on thermal ionization mass spectrometry. Everything we need is over in this right-hand diagram here. So we have our parent isotopes, uranium-235, uranium-238, our daughters, 208, 207, 206, our common lead, right, 204. We've got this radiogenic component, the red part, initial component, these blue bars. And then we're going to add the spike, remember? So we're going to dissolve the zircon, we're going to put it in solution, and then we're going to spike it with non-natural, not regularly occurring isotopes. The two that we go with are uranium-235, this green bar here, and lead-205, this green bar here. So now what we can do is we can go in, we can analyze these ratios with TIMS. We're going to measure the 206-205 ratio. We're going to measure the uranium-238 to uranium-233 ratio. If we know how much spike we've put in, we can then use those ratios to back calculate out the real amount of each one of these ratios, right? So this is the ultra high precision way to do these analyses. We can get down to uncertainties on the order of 1/10%, which is pretty amazing. So these instruments are super cool. They require a lot of prep work. They're really labor intensive, right? So ahead of time, you're doing a lot of solution chemistry. You work in these clean labs and these silly suits. You can't go put gas in your car on the way to work because that would not be chemically pure enough to go in that lab. Because it takes so much labor, the analyses are quite expensive. So both time and price-wise. So they're about $100 to $200 per individual crystal. You get really accurate data though, super precise. Okay, the second way we can do this is with SIMS, or secondary ionization mass spectrometry. The way that we're going to do this is we're going to take our unknowns, these crystals here, we're going to mount them with our standards. We're going to start by sputtering off the top of some of our standards, measuring the ratio there. We're going to do the same for unknowns, some more standards, some more unknowns, some more standards. We're going to take what we measure on the standard, we're going to correct it back to what it should be, and then we're going to apply that same correction to all of our unknowns as well. So these mass specs are massive. They take up full rooms. I think this one's Stanford and this one's Wisconsin, maybe. So this is a Kamika version. This is the shrimp version. I've never seen one of these in person. They're supposed to be just awesome. What's really cool about SIMS, why people do it, you get incredible spatial precision. So it turns out you're basically removing these, sputtering off the surface atomic layer by atomic layer. So you're getting incredibly small resolution, highly detailed studies. Okay, so laser ablation inductively coupled plasma mass spectrometry. This is what our lab does. This is what I'm most familiar with. We do this the same way. The only difference is that we're physically ablating the crystals instead of just sputtering off the surface. So we mount our standards with our unknowns. We measure the ratios of our standards and our unknowns. We correct our standards back to the ratios that they should be, which we know from TIMS. And then we use that same correction for our unknowns. So this is the mass spec that we do most of this work on. This is a new instrument's high resolution inductively coupled plasma mass spectrometer. This is actually two instruments. Mark will walk us through this in a bit. So we have a laser ablation chamber here, which is connected to the mass spec using this tiny little tie-down tube here. This is the mass spec itself. There's a torch box where there's plasma that's at the temperature of the sun, a whole bunch of focusing devices, and ultimately our detectors at the end. This one has a whole bunch of different detectors, so we're measuring, this would be each one of these detectors at the end. So we're measuring uranium, thorium, all the leads, all at the same time, as well as mercury for interferences. In this sample cell, things look like this. So basically the laser is sputtering down onto this sample surface, physically ablating material that gets mixed with carrier gas and carried on its way. Okay, so this is what one of these analyses actually looks like. So on the x-axis, we have time. On the y-axis, we have intensity. These are all of the isotopes that we're measuring. And so what you'll see here is we start off with collecting backgrounds. The laser is not on, it's just floating around in our chamber. There's concerningly a lot of this stuff, right? So that means we have to background subtract that. We have to remove that from our on-peak measurement to get the correct abundances. Laser turns on, we begin drilling through our zircon. We have a slight downhole slope to that curve as we drill down. Laser turns off, we return back to our backgrounds. One thing to notice here is that things like uranium-238 actually have a steeper downhole than things like, say, lead-207. We're actually having more trouble excavating that out of the pit. Okay, so this is kind of what I was just saying. We have to make two major corrections. One is we need to correct for our downhole. So laser turns on, these are basically seconds through time. Once we have a stable line, we can use that to correct for our downhole, the slope of that line. And then we need to make a second correction where we take this line and that the measured age, which is down like at 540 MA, and this is a standard, so we need to shift it up to its true age up here. Okay, so those are the two major corrections that are happening. And we're mounting, again, standards with unknowns in these little epoxy rounds, and pits look something like this. Okay, so once you, so this plot is for lead 206 to uranium 238. Again, remember these two things don't behave the same in the chamber, in the mass spec, anywhere along the line. So big corrections. That's not the case for lead 206 and lead 207. Those two things behave quite similarly. So yes, we need to make a small correction, but it's nowhere on the same order of corrections. We just have a slight fractionation correction. Okay, so this is important for kind of, I guess, data reporting and keeping, understanding the limits of the data that you're collecting in these labs. So we have two types of uncertainty. We have internal or random errors. These are things that affect only a single analysis. And then we have external or systematic errors. These are things that are going to affect all of our analyses. So this might be something like the fractionation factor. You know, I was reducing data, I hadn't had my coffee, I didn't do it quite right that day. Maybe it's off by 1%. What about the age of the standard? What if that's not quite right? What if we are assuming it to be something that it's just a 0.1 millimeters off? Maybe the decay constants aren't quite right. Whereas these are things that are for on single analyses. These two things often get reported at different places in your data tables. So when you go to a lab, make sure you know where to find both of these and make sure that both of them end up in whatever you ultimately publish. Okay, so we've talked about three techniques here: ID TIMS, SIMS, and laser ablation. As George mentioned at the beginning of the day, each one of these has benefits for doing different things. So ID TIMS, if you're worried about calibrating the geologic timescale, that is the method for you. You're going to get ultra high precision, but it's going to cost you both in time and in money. SIMS, if you want high spatial resolution, this is the way to go. It's much slower throughput, only about 4 analyses per hour than laser ablation, but you're going to get amazing spatial precision. So if that's the kind of question you're asking, that's the method. And then laser ablation, Kurt made our machine go really fast. So we can now do up to 1,200 unknowns per hour, which is just stupid, like insane. So we can go really, really fast, get thousands of analyses per day. But we don't quite have the accuracy or precision of TIMS. We have similar accuracy and precision to SIMS. And we don't really have much, we don't have the high spatial resolution, but we can do a lot really quickly. So the trade-offs are fun. That's the reason we do it on laser ablation systems. Okay, so some best practices here. You got to know what's best for your samples. All of you had different types of projects, which is so cool to see. But this means that it's on you to make the right choice, right? If you're asking a question about a geologic timescale, please don't come to our lab. It's very stressful. But maybe screen your analyses first in our lab, right? Choose labs that have published methods papers and data management plans. This is required for NSF reporting. Take CL images if you can, if you can. These things are so informative. Come to the lab. We love to see you guys. We love to have visitors in-house. It's been really hard with COVID not being able to do that. But we'd like to work with you on these things. We don't really want to do the work for you and then just send it to you because that's not going to benefit anyone. Ask lots of questions when you come. My main job at ALC is working with visitors, and it's really challenging when people don't ask questions because I don't know what you don't know. And so I can try to disseminate information, but most people, ask questions. We want to hear them. You'll oftentimes stump us, and that's great because we learn something. This one, generate final data tables and figures before leaving the lab. This is when we figure out what we don't know. By forcing yourself to reduce your data, to sit through it down, to reject analyses, to include analyses, this is where the decision-making happens. Even if they're cursory, I know I love Illustrator. I can spend hours in Illustrator. Just make cursory ones before you leave. Make sure when you go to publish that you include a metadata table that includes the analytical methods. For our lab, this is available online. It's on our website, but make sure that you're including that when you go to publish because otherwise people don't know how you analyze your samples. And then make sure to have lab folks check your data before you go off and publish it. So that's what I have for uranium lead methods. We are not going to talk too much about standard selection. So standards are a whole field of geochronology, right? And these are typically samples that come through a lab and are giving super reproducible ages, geochemistry, whatever. And the way that they kind of get standardized is one lab says, hey, I think this could be a good standard, and they ship it off to another lab, like a Tim's lab. And eventually somebody writes a methods paper that has multiple labs that have all run similar analyses on the same thing. And hopefully they're getting similar results. In terms of what you guys need to know as users, there are different age standards. And if you are running, let's say Kurt has samples from the basin and range, and they're chock full of Miocene zircons. The youngest standard that we typically mount on our mounts is 420 million years old. If you're running Miocene grains, hey, it would be great to have like an Eocene standard on there, something a little bit closer to the same age. So do let us know, do let the lab that you're working with know generally what age you think things are going to be so that we can mount appropriate standards. Do you have additional questions?
No, it's just particularly germane to calcite.
Yeah, that's a great point. And so we will talk about that a little bit in the Petrocon area. So most of the standards that we use for geochronology, we want them to be what we call matrix matched. That means that they are made out of the same mineral or material as what we want to measure. So I'm not going to use a zircon standard to measure Kurt's rutile. That's why he's carrying around rutile standards with him. Okay. Yeah, finding standards is hard. It takes a lot of time. It takes a lot of just like mounting things up, zapping a bunch of things, seeing what's reproducible and what's not. I know that the calcite world is really struggling with this. I can put you in touch with some people. I don't know if that would be useful, but I know several people that are working on that actively and also struggling with it. Any other questions? Yeah.
I'm just curious. You don't want to. How are you able to ablate so many grains in an hour?
So the question was, how do we ablate so many grains in an hour?
I'll touch on that when we do the live.
And Kurt will touch on that later today. Any other questions in here? You guys got questions online? George, how are we going?
No questions online, but I'll go ahead and jump in and talk a little bit about standards. As you may know, our lab is one of the one of the national facilities in the US. We're funded by the National Science Foundation to help people come to our lab, but also to help other labs. And so we've assembled a set of 10 standards that we put together into a packet, and we send off to pretty much anybody in the world who wants to do kind of a comparison of those different standards, just to make sure they know how their lab is doing. The standards range from 3.6 billion years old to 26 million years old. So pretty much the whole range of time that you can do with uranium lead. These are all zircons. And we put 100 crystals in each little packet, and there's 10 of those little standards that come in a set. This was a project we did a few years ago with undergraduate students. We asked them to pick 100,000 zircon grains, if you could imagine that, and put them into these little packets. And so far, we've distributed these packets to about 105 different labs around the world. So whichever lab you end up going to, ask if they have a set of these standard zircons. And if not, just contact me and I'll be very pleased to send them to you, no cost. We just send them out right away. And then the lab can take those standards and run them and just make sure they're getting the right ages from 3.6 billion all the way to 26 million. So we're kind of one of the world distribution centers for zircon standards. Now with Mauricio coming into the lab, we're hoping to move into titanite and monazite. We've done a little bit of standard work for those minerals. Probably bedelliite also, and rutile and apatite. I'm not sure we have the capacity to do all those different minerals, but we're going to start exploring how we can help the community with these other phases. So hopefully that's useful info regarding standards.
Thank you, George. Okay, one last call for questions. You can always return to any of this. Okay, so what we're going to do now is we're going to take